Welcome back, students. This is the session 2 from the chapter of circular motion, and this session is in continuation of the session number 1. So, in this session, I will be discussing in brief about the dynamics of circular motion. So, in the previous session, we have discussed that the circular motion can be uniform as well as it can be non-uniform. Now, in the case of a uniform circular motion, the linear or the tangential velocity is same. It remains the same, it doesn't change. And in the case of a non-uniform circular motion, this tangential velocity, or you can say the linear velocity, is not constant. It keeps on changing. So first we will take up the uniform circular motion. Uniform circular motion. So in the uniform circular motion, as I have just told you, that this tangential velocity or the linear velocity, it remains constant. Now in the previous session we have seen that the tangential velocity v is equal to r omega, where omega is the angular velocity, r is the radius of the circular path, and v is the tangential velocity, or it can be also called as the linear velocity. So v is equal to r omega. Now if in the case of a uniform circular motion, if v is constant, then dv upon dt will be equal to 0. Because now what is dv upon dt? This is the tangential acceleration. So if v is constant, then tangential acceleration will be 0. Or we can say that the tangential acceleration, which is denoted by at, this will be equal to 0. I also told you that in the case of a circular motion, or you can say a body moves in a circular motion if the centripetal force is equal to the centrifugal force. Now this centripetal force is given by is equal to m v square by r. We will be discussing about this centripetal force and the centrifugal force in detail in the subsequent sessions also. So the centripetal force is given by mv square by r, and now force is equal to mass into acceleration. So it implies that the centripetal acceleration, here I have written here, that is there is one body which is moving in the circle. So this at is the tangential acceleration, and AC or AR. AC is the centripetal acceleration, which is also called the radial acceleration. So here, if you just from this relation, we get that A is the centripetal acceleration. So AC, or we can also say as AR. This is equal to V square by R. It is also called the radial acceleration, and it is directed towards the center of the circular path, as I have indicated here with an arrow. So in the case of uniform circular motion, the tangential acceleration is 0 and the centripetal acceleration is equal to v square by r. So it implies that the resultant acceleration in the case of a uniform motion, this will be is equal to the resultant acceleration is basically equal to at square plus AC or AR square. This is the resultant acceleration in case of a circular motion. Now in the case of a uniform circular motion, this tangential acceleration is 0. So the resultant acceleration will be equal to AC, and this is equal to V square upon R. This can also be written as, since V is equal to R omega, so we can write this as R square omega square upon R, or we can say that the this resultant acceleration, which will be equal to the centripetal acceleration or the radial acceleration, this will be equal to R omega square also. So this is the resultant acceleration, and this resultant acceleration will be directed towards the center of the circular path. So this is the first case. Now I will be taking the case when the motion is not uniform. Motion is, this is now I will be taking the case of it. It's a which we can call as a non-uniform motion. So in the case of a non-uniform motion, the tangential velocity, or you can say the tangential velocity V keeps on changing with time. Okay, now we know that V is equal to R omega. Here R is the radius of the circular path, so it is a constant value. So we can say that it implies that V is directly proportional to omega. That is, if V is changing, then this angular omega is the angular velocity. So this velocity will also change. Now dV upon dt is equal to what will this will be equal to R, or R is a constant. So dV upon dt will be equal to R d omega upon dt. In the previous session, I have told you this d omega upon dt is the angular acceleration, and this is denoted by alpha. Okay? So this is denoted by alpha. Alpha is the angular acceleration, and dV upon dt is what? It is the tangential acceleration. So AT is equal to R into alpha. So this is an important relation. This is an important relation in when this circular motion is non-uniform. So AT is equal to, I'm just writing it here, that AT is equal to R into alpha. Okay? Now, as we know that in the case of this circular motion, the centripetal acceleration or the radial acceleration is directed towards the center, and its value is given by AC or AR. This is equal to V square upon R, and this is also equal to R omega square. And this is directed towards the center. This tangential acceleration is directed along the tangent at a particular point. So I have already drawn the direction of this tangential acceleration as indicated by this arrow, and this arrow is indicating the direction of the centripetal acceleration or the radial acceleration. So in this case, the resultant acceleration will be equal to under root of, as I have just told you, that the resultant acceleration will be equal to AT square plus AC or AR whole square. So resultant acceleration, so this resultant acceleration is equal to under root of AT square. Now AT is equal to R alpha whole square plus V AC, that is the radial acceleration or the centripetal acceleration. So this is equal to V square upon R. So V square upon R whole square so V square upon R whole square, and so this can be written as under root of R square alpha square plus V to the power 4 divided by R square, or it can also be written as R square alpha square plus see, this radial acceleration is equal to V square upon R, so I have written it as V4 upon V to the power 4 divided by R square. But this can also be written, and this AC can also be written as is also equal to R omega square. So I will be just squaring this term, so I will be getting as R square omega 4. Okay, if I put this value here, then it will be equal to R square and into omega to the power 4. So finally, if I take this R square as common, so I will be getting this resultant acceleration as R alpha square plus omega 4, omega to the power 4. So this is the resultant acceleration in case of a non-uniform circular motion. That is, this is equal to under root of R square alpha square plus V to the power 4 divided by R square, or it can also be written as R into under root of alpha square plus this omega square. Oh sorry, omega 4. So this is an important relation. This one is an important relation, and this one is also an important relation. Apart from that, this is an important relation which you all have to remember. Similarly, this centripetal acceleration, this has to be remembered. So these are some of the important formulas with respect to this session, that is dynamics of circular motion, or you can say with respect to the topic of dynamics of circular motion. So in the next session, I will be discussing about the forces in the circular motion. So till then, have a nice day. Bye.